All right, everyone, we had two bits of homework last night. First one was on page 592, questions 1 to 2, 5 to 8, 10 to 16. Second one was on worksheet number 11. Let's take a look at 592 first. Are there any issues with any of those questions, please, on page 592? Patrick? 12? Yep, Lauren? 16? 12, 16? 11, 12, 16? Is that it? Okay. All right, let's take a look then at 6, 11, 12, and 16. 6 says, what's the shape of the magnetic field around a straight current-carrying conductor? A is a fairly straightforward one. What's the shape of the magnetic field surrounding a straight current-carrying conductor? In other words, around a straight wire, as long as it has a current going through it. It's the shape of it. Quickly, one word. Circle. Circular, right? It's a series of concentric circles. We know they get further and further apart the further they get away from the producer, which is this current-carrying wire here. Okay, it shows us that the field is getting weaker and weaker. But basically, you said it, Paige, it's circular. Okay? What about within the coil of a conducting wire? They're saying within. So within means inside. Inside that current-carrying conductor, we don't even know which way the current's going right now, so I don't even care about the direction. What's the shape of it? It's a straight line. Inside, it's a straight line, either pointing towards the right or pointing towards the left, right? Points toward whichever end is the North Pole and away from whichever end is the South Pole. All right, next question was number 12. It says, why does dropping or heating a bar magnet decrease its magnetic properties? Anyone have an answer for this one? Why does dropping or heating a bar magnet decrease its magnetic properties, Max? Yeah, essentially you're causing the domains to become less aligned when you drop it or when you heat it. Basically, when you're pumping that energy into it, you're causing these domains to scramble a little bit, point in more random directions as opposed to aligned directions. I guess that was number 12. We skipped number 11. Let's go back to number 11. It says, using the domain theory, explain the following observations. A magnet attracts an unmagnetized ferromagnetic material. Who can explain question A there in terms of the domain theory? Why does a magnet attract an unmagnetized ferromagnetic material? And we talked about that as the third law of magnetism, right? We said that magnets attract non-magnetized ferromagnetic materials because of this. What does it do, Max? Good. You're temporarily aligning the domains. It's induction. You're inducing a temporary alignment of the domains, just like when charged objects attract neutral objects, you are inducing a temporary separation of charge. Stroking a nail with a magnet magnetizes the nail. You're pretty much doing the same thing there, right? It's closer in proximity, so you're going to have a stronger effect, but what you're doing is having domains from the magnet inducing the domains in this nail to become aligned as well. And finally, a metal table leg affects a compass. Why does a metal table leg affect a compass? Some metal table legs do, not all. Most of them do, because most of them are made out of, most metal table legs are made out of what? Steel, right? Most of them were made out of steel. So why does a steel table leg affect a magnetic compass? It's ferromagnetic, and what? The compass is a magnet, so basically it's question A, right? A magnet is attracting an unmagnetized ferromagnetic material. The compass is the magnet, okay? It's attracting the table leg. Well, the table leg is also attracting the compass, okay? Because if object A applies a force on object B applies an equal and opposite force on object A. So if the compass attracts the table leg, then the table leg will attract the compass, and it's going to wreak havoc with the direction of the compass needle there. Finally, we had question number 16. Oh, that's a good question. Somebody asked me about that yesterday. Good question. Kind of a hard one to explain, though. If a current-carrying wire is bent into a loop, why is the magnetic field stronger inside the loop than outside the loop? Does anybody have an answer for that they can give me before I give my answer? Shorter distance between the poles? No. No. The polarity is, we got a north end and a south end, and there's only two poles. So the distance between the poles is the same, regardless of whether you're looking at inside or outside, right? It's a good guess, but. Anyone? Paige? Yeah. Yeah. Field's adding up on the what, sorry? No, the other way around. Field's adding up on the inside. Gives us a stronger magnetic field, right? So you're on the right track there, for sure. So this is our coil. And let's say that we've got, here, let me draw some wires here. So we've got a coil here now with some wires that are like this. Okay, each of those wires generates its own magnetic field. Now, when we say, here, let's make the current up in the front. Doesn't really matter whether it's up in the front or down in the front. When we're analyzing a coil of wire and trying to find the direction of the magnetic field, we're going to normally use the, not the wire grasp rule, but the coil rule, right? Which says stick your fingers in the direction of the current, and thumb's going to point in the direction of the magnetic field. That tells us what the direction of the magnetic field is, and at this end, the right side is a north pole and the left side is a south pole. It doesn't answer this question. So let's go back to the wire grasp rule now, that first rule that we learned. Okay, we can use that for coils as well. It's applicable anytime you have a wire with a current going through it. It's just a little bit harder to do when you have that wire changing direction like you do in a coil here. So let's pretend now that we have this first wire, wire number 1, with an electric current going up in the front. Okay, we're going to use the wire grasp rule this time. Thumb in the direction of the current this time, fingers in the direction of the magnetic field. So that would mean, okay, inside the coil, the magnetic field would point towards the right, okay, and then outside the coil, the magnetic field would point towards the left. Okay, if I look at this one, okay, the magnetic field is going inside the coil. This one, it's going inside the coil to the right. This one, it's going inside the coil to the right. Those all add up, right, to give me a stronger magnetic field. But outside the coil, they add up there too. So why is it stronger inside than outside? Because let's do it on the back now. If we do it on the back, the magnetic field caused by the wire in the back points in the same direction inside the coil. That adds up further to make it even stronger inside the coil. Now, we've got a magnetic field outside the coil as well, but it doesn't add up with the magnetic field outside the coil in the front. Does that make sense? So the magnetic field caused from the wire in the front adds up on the inside and the outside. The magnetic field caused by the wire in the back adds up on the inside and the outside. But the outside is a different outside. It's the back instead of the front. The inside is the same inside. So we get, if we just look at the front and the back, we get double the magnetic field inside as outside because we've got that magnetic field caused by the front and the back going in the inside. Now the reality is we could look at it in the top and the bottom as well, which would increase the strength even further, right? But you see the effect there by just looking at the front and the back. Who asked that question, number 16? Is that okay? All right. No other questions on that? All right, then let's take a look at worksheet number 11. I'll put the answers up here, and we can take a look at those and see which ones you need gone over from that sheet. A little messy in some places here, but I think you can still read it. If you have any questions, just ask me here. Okay, questions 1 to 5. Just look at the answers. Don't try to work through it right now. Okay, if you have a wrong answer, just kind of make a little note, and then you can ask me once we're finished giving you the answers here. Okay, 1 to 5. Sorry, 1 to 6, I guess. Notice in a question like number 2, our answer is expressed down the page. Okay, it's relative to the page. Why? Because it talks about the electron going into the page. The frame of reference in the question is the page. In a question like number 4, we're not saying up toward the top of the page. We're saying up. Why? Why aren't we referencing the page in question number 4? Because the question talks about north, south, east, west. So if we're talking about the page in the question, then our answer has to reflect that. If we're talking about north, south, east, west in the question, then our answer has to be relative to the earth as opposed to relative to the page. Any issues with 1 to 6 here before we move on? They all good? Everybody know why 5 and 6 have no force? They're parallel. In the first case, the field is parallel to the direction of the particle. And in the second case, question number 6, you got an alpha particle going out of the page, magnetic field going into the page. They're 180 degrees to each other, but that's still parallel, right? So the magnetic force would still be 0. 7, 8, 9. I put a little star by number 7 because I assumed when we did this, number 7, geographic north. Okay, it would normally in a test question it would be a little bit more clear what we meant by that, whether it was geographic north or magnetic north. If you assumed magnetic north, what should you have gotten for an answer there? It would be down, right? So it would be opposite to that. So I wouldn't mark that wrong. Okay, if you assumed magnetic north, then that's a reasonable assumption for that question. It's just that I assumed geographic north. How does it give you up? Okay, so you want to take a look at that one? Number 7 says an electron traveling to the east. That's going to be to the east, right? And that's going to be geographic north, okay, or magnetic south. That's west, and that is magnetic north or geographic south, right? Now, by the way, if you're in a room writing this exam, it'll likely be the cafeteria. Okay, and you're having a little bit of trouble orienting yourself, so that you're not exactly sure which is north, south, east, or west, right, Matt? Then make it up. Just assume that forward is north, backward is south, or geographic north and geographic south. And then to your right is east and to your left is west. It doesn't really matter if it's real or not, okay? As long as you're consistent with your north, south, east, west. Okay, we're going to say that that's north, geographic north, that's geographic south, east, and west. So we've got a particle, an electron going to the east. I'm going to stick my thumb to the east, my left thumb to the east. My fingers are going to point in the direction of the magnetic field, and the magnetic field here is going towards geographic north or magnetic south, right? So my fingers are going to point this way, which means, the magnetic force is to the north, sorry. Okay, so I'm going to stick my thumb to the east, my palm towards magnetic south or geographic north. My fingers are going to point up, right? We're not saying out of the page, because the frame of reference is north, south, east, west. It's pointing out of the earth. If you want to say that, you could, okay, or you could just say up. Now, if you assume the other north, magnetic north, which is down there towards Antarctica, right? Then we would say my palm would point towards magnetic north, and my fingers would point in the direction of the magnetic field, which would be not south, down, right? Down towards the earth. Okay, south, magnetic south would be that way, okay, down towards the earth, right? So both answers would be correct. It just depends upon how you interpreted the question, okay? There's not really one right way to interpret that. These other ones okay? Notice in question number 8, again, we talked about toward the top of the page. Why? Because we weren't talking about the earth as our frame of reference here, north, south, east, west. We were talking about the page as our frame of reference. So we have to express our answer that way as well. Finally, we had 10, 11 here. Question like number 10, some people get messed up on that a little bit because we're looking for the acceleration, but you know what to do with that now, right? You want to find an acceleration in physics 30, get a force. Electric force, magnetic force, gravitational force, whatever force it happens to be, and then simply divide that force by mass. In question number 11, we just had to rearrange there. Any issues with either of those? Okay, finally, question number 12. Similar one here, except that this time we had acceleration instead of trying to find it. We're just going to set the magnetic force equal to m times a. Okay, we could have done that separately if we wanted. We could have said F is equal to m times a, get the value for force, and then set it equal to QVB. I just chose to put it all together. It doesn't really matter. Any issues with that one? I see a couple of people actually writing this one down. Does it make sense as you're writing it down? If it doesn't make sense, I don't want you to ask me about it. Don't just copy it down. Ask me the question. Yeah. Yesterday, we went a little bit further with charges and magnetic fields. We know that they experience a magnetic force because of the magnetic field that they produce and the external magnetic field. Two magnetic fields are going to interact with each other to produce a force. Magnetic field caused by one, magnetic field that was already there, going to be a force. Now, we figured out the direction of that force a couple of days ago using the hand rule for deflection, the third hand rule, the deflection rule. It essentially said thumb in the direction of the particle, fingers in the direction of the field, palm points in the direction of the force. And we did that a couple of times in our homework questions, right? Thumb, fingers, palm points in the direction of the force. Yesterday, we took that a step further, though, and said, we talked about the shape of the path of the particle as it goes through a magnetic field. The shape of the path that the particle always takes as it goes through that magnetic field. Not just sometimes, always. If you have a uniform magnetic field here, today we'll represent it by dots. Those dots mean what? Out of the page. If we have a uniform magnetic field with the dots going out of the page, okay, magnetic field going out of the page, and we have, let's say, a negatively charged particle going in towards, into that magnetic field, then it's going to experience a force of deflection. That initial force of deflection will be thumb to the right, fingers out of the page, palm points upwards. That initial deflection will be upwards. But that's going to cause the particle to go over here now. Now there's going to be a force that's up and to the right. Okay, now the particle is going to go over here. And so on. Oops, messing this all up here now. Force is going to go over this way. We notice the shape of this path is always going to be circular. It doesn't look much like a circle, but it's supposed to be. Okay? The shape of the path is always going to be circular, always, as long as it's in the magnetic field. Now, is it possible for it to go all the way out the other side? What would make it go out the other side? Let's draw that again. Let's say we had that magnetic field. The path was curving upwards as the particle goes into this magnetic field. Is it possible to go all the way out the other side instead of curving around like this, like we showed you yesterday? Is it, Logan? Okay. If the force of gravity acting on it balanced the magnetic force, then yes, it would. That's not what I was looking for, actually, but you're absolutely right. Okay, it would. Let's assume, though, that we don't have a force of gravity there. It's an electron, and there is a force of gravity, but it's so ridiculously small that it doesn't really matter. Is there a way for it to go through the other side? Not necessarily straight through, but make it to the other side. Travis? If it's moving faster. There's two ways here. Okay, one, if it's moving faster. If it's moving so fast that it takes a bigger loop. You guys know that in your car, when you drive faster around a turn, the radius of that turn necessarily becomes bigger, right? As an electron or whatever goes faster through this magnetic field, the radius is going to become bigger. And if the radius is big enough, it's not going to go in a half circle. It's going to go in a little bit of an arc like this and just scoot out the other side. So if it's going faster, you can make that happen. What's the other way of making that happen? Mass. Decrease the force. Yeah, that's where I'm trying to get to there. Decrease the force, the magnetic force. Now, how could you decrease the magnetic force? How about decrease the magnetic field strength, right? Okay, if you decrease the magnetic field strength, then that's going to affect it as well. All right, we talked about analyzing this. While it's in the magnetic field, for this section right here, okay, we're allowed to use the equation that we learned a couple of days ago, F is equal to QVB, but we're also allowed to use what other equation? FC, yeah. FC is equal to mv squared over r. The equation that doesn't appear on our data sheet, right? Why are we allowed to use that one? Yeah, if it's going in a circle, even if it's not a complete circle, it's experiencing a centripetal force while it's in that circle. Even if it's only for 1/16 of a turn, Okay, it's still going to experience the centripetal force. So we're allowed to use that now. We're also allowed to use the combination of those two. Fc is equal to Fm. So whatever seems to fit. Generally, if the question talks about a radius, you're going to use the middle one, the end one. Okay, generally, if it doesn't talk about a radius, you're going to use this one. Okay, usually it's either this one or a combination of the two, but every once in a while it might be just the second one. Okay, just look at your givens, see which one fits, right? Now, you don't need to draw this unless you want to. This is another application, okay, that we talk about. Okay, one that you probably won't see on an exam, but you might. It's just to get you thinking about it. This is what we call a cyclotron. Okay, a cyclotron is essentially a particle accelerator. Now, we'll talk more about particle accelerators in literally our last couple of days in class in Physics 30, but we'll give you the essence of it right now. Okay, sometimes we're curious. We're by nature curious people. So sometimes we want to find out things that nobody else has ever found out. Sometimes we might want to take a peek inside a proton. Okay, can a proton can be broken down any further beyond a proton? You've learned until this point, right, that protons, neutrons, and electrons are fundamental subatomic particles. Well, that's not quite true, actually. In two of those cases, they're not fundamental particles. Let's take a proton. Let's say we want to find out what's inside a proton. What do? Well, we can't just open up the door and look inside the proton. So we do what any good man would do. We break it. We want to find out what's inside. We break it. We smash it. Okay, that's what guys do, right? Hey, I'm curious. I want to find out what's inside this. Let's smash it. Let's smash it open. Girls are more patient and more intelligent about their thoughts. Guys are just brute force and smash it open. This is like a guy's machine, right? Because that's the whole point. Get these protons going really, really fast and then smash it into something. Break it open and see what's inside. Okay, we'll talk more detail about that in our last couple of days of class. Okay. I'm sorry? Yes. So how do they do this? Well, there's a couple of different particle accelerators. There's cyclotrons, like this. There's also linear accelerators. This is highly effective because it allows the particles to use the same field to accelerate it to get it going faster over and over and over again. So here's what happens. There's an ion source. This is the ion source right here. This is where we put our ions, or a proton, or whatever ion that we're trying to accelerate. Okay, and that ion experiences. You can see right here, in the gap here, there's an electric field region. So it experiences an electric field. What happens to a charged particle when it experiences an electric field? Speeds up. Right? A charged particle accelerates across the potential difference. It's like a car going down a hill. So now we've got this charged particle speeding up a little bit. It's moving, it speeds up a little bit. Now it goes through a magnetic field. Well, what happens to the charged particle as it goes through the magnetic field? Changes direction, right? It goes in a circular path. It's going to go in a circular path this way. And then what happens when it reaches this electric field again? Speeds up, goes a little bit faster, goes in a circular path, goes a little bit faster, goes in a circular path. So the radius of the circle, every time it goes through the electric field, keeps getting bigger and bigger and bigger, right? Because it keeps going faster and faster and faster. Travis mentioned it earlier when we were talking about how could it go out the other side. Make it go faster. Okay? We increase the radius of the path every time we make it go faster. So that's why instead of going in complete circles here, it's going in a half a circle, and then another half a circle, but with a bigger radius. It's spiraling outwards because we keep making it go faster and faster every time we go across that electric field. So the magnetic field keeps it inside these circles, okay, in this relatively small area, so that it keeps going across these electric fields and going faster and faster and faster. Faster, 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 and then at some point we let it go out and then we smash it into something. Okay, maybe we smash it into another proton. Maybe we smash it into some kind of other target and see what's inside. Now, I got a question for you regarding this. Okay? There must be a magnetic field that's causing this ion, whatever it is, to go in a circular path. Let's assume that this ion is positive. Okay, you could put something negative in there as well, but let's assume in this case that it's positive. Which way does the magnetic field need to be in order to cause this particle to go in the circle that it's going in? Which way does the magnetic field need to be? Okay, I'm going to give you about 30 seconds kind of at your desk yourself to see if you can come up with an answer to that question. Okay, the charged particle is going like this. Which way does the magnetic field need to be in order to cause that to happen? Matt says the magnetic field is going to be inwards. Let's check that, okay? We're going to find this by the hand rule for deflection, but it's going to be the right-hand rule because it's a positive particle, right? So we stick our thumb in the direction of the particle, fingers in the direction of the field. Oh, we don't know which way the field is. Okay, palm in the direction of the force. Oh, wait, we don't know which way the force is. We don't even know which way the particle is going because it's going in all kinds of different directions, right? We're going to pick a place. Okay, let's pick this place right here. Okay, right here. Which way is the particle going at that spot? Upwards, right? Which way is the magnetic force at that spot? To the left, toward the center of the circle. So the particle at that spot is going upwards, thumb upwards, palm towards the center of the circle. Fingers are going to point into the page. Matt, is that what you said? Good, you're right. Force is going to be into the page. Now, what if you had picked a different spot? What if we had picked, I don't know, this spot right here? Okay, the velocity of the particle is going this way at that point, right? The magnetic force is into the center. Now we're going to say thumb, palm, fingers are still pointing inwards. So it doesn't matter where you pick it, right? The magnetic field is going to be inwards any way you look at it. Now, what kind of magnetic field would you have to have if this was a negative particle? Out of the page, right? Make sense, guys? Yes? All right. We're going to give you a couple of minutes here right now to take a look at a few of the questions on worksheet number 12. Only about 5 minutes, okay? Only about 5 minutes, just so that we can make sure that you're kind of on the right track here. And then we're going to move on and do a couple multiple choice questions. All right, I want you to take a quick peek, everyone, at two multiple choice questions. They're page, not sure what page they're on, actually. The multiple choice number 75 and 76, and they both go with the scenario that we see right here about the Earth's magnetic field. Number 75 and 76. We want to find a direction. Okay, first of all, so it's going to be a hand rule, and then the second one is going to involve a calculation, where we're going to try to find a radius. See what you can do with those two questions here right now. Let's submit them as multiple choice number 1 and 2, please. Sorry, guys. It is multiple choice number 1 and numeric response number 1, not multiple choice number 1 and 2. Okay. So multiple choice 1, numeric response number 1. Just submit them both together. Okay. So 2 answers, kind of in one there. All right, everyone. Question 75 asks us for the protons in the solar wind, which direction they experience a magnetic force. Let's go back to the info here. We've got protons in the solar wind, positive particles going to the right. We have a magnetic field that looks like a bar magnet, right? Looks like the magnetic field surrounding a bar magnet. Notice at the top here, Northern Canada says magnetic south. That's not unexpected, right? We should expect to see that. At this point, the magnetic field is pointing upwards, at the point where the protons enter the Earth's magnetic field. We're going to use our right hand here because it's a positive particle, protons. So right-hand rule for deflection, thumb in the direction of the particle, fingers in the direction of the field, which point upward. At this point, okay, somewhere else they point in a different direction, but at this point they point upward. Thumb, fingers, palm points, which way? Out of the page. So the answer for this one would be out of the page, or out of the plane of the page. 76 says assume the velocity of the solar wind particles is perpendicular to the magnetic field, and it looks like it is at that point. We want to know the radius of the path, the radius of the circular path that the protons in the solar wind follow. We know that we're allowed to use F is equal to QVB because the charged particles are in a magnetic field. But we also know that whenever they talk about a radius in the context of a charged particle in a magnetic field, we're almost certainly going to do Fc equals Fm. Okay, we could do F is equal to mv squared over r. We could do F is equal to QVB. But usually in that situation, we're going to combine them. It becomes mv squared over r equals QVB. One of the v's cancels. Not both of them, but one of the v's in each term, each side cancels. And we're looking for r. So the r goes up here, and the QB goes down. So effectively cross-multiplying. R becomes equal to mv over QB. M is the mass of a proton, so it's 1.67 times 10 to the minus 27 times the speed of the proton, which is given to us, I think, in this information, 8 times 10 to the 5 meters per second. The charge of the proton is 1.6 times 10 to the minus 19. And the magnetic field strength should be given to me in that question as well. 1.1 times 10 to the minus 7 Tesla. What do we get when we do that math? (7.59 times 10 to the 4 meters. Anybody else get that? All right. So how do we express that? If they ask it b times 10 to the w, then b would be 7.59. If they ask a decimal bc times 10 to the d, then we're looking for 7.594. All right? Got it? Okay, so what's your homework for tomorrow? Review, yeah. Study for that momentum test. What's your homework for Monday as it stands right now? Worksheet number 12. Yeah. All right. That's it for today, guys.